right, welcome back, everyone. I should probably take this opportunity to introduce myself. For those who don't know me, I am Alicia Gaudette. I am our Educational Services Manager here at MMA. And it is my pleasure to next introduce Mark Carter, who is the Vice President for Smart Solutions for RealTerm Energy. And he's going to talk to us today about using artificial intelligence to lower building operating costs and reduce our environmental impacts. As some of you may know, RealTerm is a leader in smart infrastructure solutions, and RealTerm really specializes in small and mid-sized communities. Mark is located right here in Maine, went to UMaine at Orono, and was served in the Army Corps of Engineers. And he has a particular knowledge and talent for public-private partnerships, which I'm sure many of you will find interesting. So without further ado, I think I will hand things over to Mark. Welcome.
Thank you very much for that warm welcome, Alicia. I really appreciate it. And it's a great day here in Powell, Maine. So I hope it's equally as pleasant where you're dialing in from. So, and hopefully we'll all be together again in person up to Augusta this fall. I'm looking forward to that. So with that, I am going to start. And I will share my screen. If you could just confirm that that looks okay.
Yeah, if you want to switch it out of presenter mode, Mark, and then you should be good. There you go.
There we go. Great. Well, thank you, everyone. So today's talk will be regarding artificial intelligence to lower building operating costs and environmental impact. For the agenda, I have 4 items. First, I'm going to spend the next 30 to 45 minutes together, kind of an overview of why it particularly matters. And then I'll get into the fundamentals of artificial intelligence. And then I'll talk more specifically about using artificial intelligence applications within building HVAC, which is a heating, ventilation, and air conditioning system. And I'll end with a case study. So with that, I'll just start with the first topic of why did this matter. And a lot of it goes back to global warming. So if you look at greenhouse gases, CO2 particularly, it helps trap the energy from the sun in the earth, and we're, I'm sure, all quite educated about the effects of global warming and the impact that it's having on the earth and the rising temperatures. But what does that have to do with HVAC? If you actually look at the breakout of energy consumption in the United States, buildings make up roughly 40% of that. And within that 40%, over 40% of that portion, or 17% of the total, is directly attributable to the heating, ventilation, and air conditioning systems of buildings. So it's a tremendous target. But there's tremendous challenges as well for building owners. You know, roughly half the energy that's used in a building is consumed by the HVAC system, but a tremendous amount of that is waste. And it's not particularly easy to upgrade systems and to implement energy-saving measures within the buildings. It tends to be very costly, a lot of upfront capital cost, and it can be very challenging for building owners from a financial perspective. Certainly, last but not least, is the tremendous amount of both state and federal legislation and focus on reducing greenhouse gases. So just here in the state of Maine, in 2019, there was a couple LD 1679 and 1543, both really at the core of it is trying to go after the efficiency of buildings and the release of greenhouse gases. So with that, I'll switch over and actually talk a little bit about artificial intelligence. It's a very broad topic. You could spend days reading about it, but I'll try to get a very high level view of the different types of artificial intelligence and really what it means. So at the highest level from a definition standpoint, it's really anything that a computer or machine can do that would normally have thought to require some form of intelligence. And there's a whole branch of science. Artificial intelligence is a lot of universities now that actually have courses and degrees that are specified for the development and programming of artificial intelligence. From a category standpoint, there's a lot of ways to actually classify different types of artificial intelligence. In one way, there's a type 1 through 4 methodology. And the first one is really kind of the entry level artificial intelligence, which is purely reactive. So this is really kind of the most basic form of AI. It has the ability to do a particular task and do that task particularly well. And an example of that would be early on would be IBM's Deep Blue, right? So it was taught how to play chess. It improved itself over time, and eventually it was virtually unbeatable by any human. That's type 1, and that's been around for several decades at this point. Where we currently are, and where you see the most of the activity in the AI realm, is really now in type 2, and that's kind of where most of the industry is, and that's actually a limited memory capability. So not only can it do one particular task well, but now you can actually feed additional information, and it's going to learn over time from its mistakes and be able to incorporate that to be better. And examples of that are, self-driving vehicles, as well as chatbots. So that's really where we are today. Eventually, we'll get to type 3, and that's really just on the beginning of the development phase, and it's probably 15 to 20 years out. But this is where we actually get to the point where they have the capacity to understand human thought and emotions. And so that's really emblematical if you think of the Star Wars series C-3PO, where not only could you communicate to humans, but they could actually distinguish whether somebody was hurt, whether they're sad, happy. They have those abilities. And I think there's a tremendous amount of opportunity in our society for that, definitely in the medical industry. You think from nursing or in-home care, not just having a robot that can provide certain medicines or keep track, but also be able to distinguish how the patient is feeling, how their moods are. It'd be very, very valuable in the long term. Of course, the last one is the one that gets the majority of the attention is the type 4. And luckily, this is probably quite some time away, but that's the self-aware artificial intelligence. And that's where a lot of the movies, like in Ex Machina, or you look at the Terminator movies, that's when the robots become self-aware and they start making their own decisions, and hopefully those decisions don't exclude us. So that's the overview from the 4 different types. But artificial intelligence can also be classified in other ways. So artificial intelligence is an umbrella term, right? So there's different versions of artificial intelligence that are more complex. So one example is machine learning. So machine learning actually improves at a given task with experience, but that's one form of artificial intelligence. And then the most complex ones currently are deep learning. So you think deep neural networks. And those are the ones that are the most productive. And those are the ones that really allow for the high-end applications like self-driving vehicles. So we've talked about artificial intelligence. If you want to get a broad overview of machine learning, if you look, there's kind of 3 different categories. There's unsupervised learning, there's supervised learning, and a reinforcement learning. But if you look, the number of applications is tremendous. So for anyone that doesn't think that artificial intelligence is touching our lives on a daily basis, I can assure you that's incorrect. Everything from the banking industry to self-driving cars, gaming, and also in the medical industry, from image classification, looking at x-rays. They're using a lot of artificial intelligence for that. And when we get one level deeper into the deep learning, there's really 2 different types. There's a deep convolutional networks and deep recurrent networks. So they each have kind of a special talent of what they can do. The first one, your convolutional neural networks, are really good at computer vision, right? So this is used in self-driving cars to actually be able to identify a person versus a vehicle versus a deer. It's very, very important that it can do that. It can do that quickly. And also, I mentioned before, X-ray imaging, where a doctor may look at thousands and thousands of X-rays over his or her career. You can take an artificial intelligence model and load in millions. So it can learn from that, and it can distinguish on an X-ray, what is cancerous, what is not, different types of tumors. It's particularly effective at doing that. So That's really the talent or the capabilities of a convolutional neural network. The other type are recurrent neural networks, and that's good with time series based events. So think of things such as chatbots or even HVAC equipment, right? So your environment, your zone temperatures in your building are going to change over time. So really within the deep learning aspect, recurrent neural networks are what's required to actually have an impact on HVAC equipment in buildings. Well, with that, I'll move over into that category and talk a little bit about how AI can be used within buildings, specifically for the heating, ventilation, and air conditioning system. So first, it's important to kind of understand what actually feeds the neural networks in the artificial intelligence brain to actually come up with its predictions and its expected output controls. So first, it's going to take data from the building itself, sensor data, whether the temperature, humidity, what the occupancy is. It's going to look at the weather data. It's going to look at utility rates and tariffs. It's also going to pull from its own memory. So over time, an artificial intelligence within a building is going to become more and more effective because it's seen these activities before. So if it knows on a particular day with a particular forecast, sun direction, wind speed, it can actually improve its modeling and its calculations. So it takes all those into consideration when it's making its control. And then it's going to come up and it's going to make a predictive model of what the zone temperature is going to be in every zone of your building. And then from that, knowing 2+ hours out in the future, it can start making adjustments now as opposed to waiting for your temperature to get too hot or too cold. And that's what helps save the energy. And it also makes the buildings more comfortable because you're not having the huge temperature swings. So as I mentioned, it does come up with modeling. And that's really the key to this. If you can't model it, then there's, taking control action on bad data is not very advisable. So you really have to be 98, 99% accurate of a zone temperature 2 hours plus into the future. And that's really the baseline of what's the artificial intelligence algorithm is doing before it actually makes a control move. So knowing what that temperature is going to be in the future, how that plays out is that in a typical HVAC system, you're going to have a cooling set point and a heating set point. So for example, if your zone temperature is set for 70 degrees Fahrenheit, your cooling set point may be 72 degrees. So if it hits 72, it's too warm. It's going to engage the HVAC equipment to actually cool the building down. And conversely, your heating set point, that could be 68 degrees. So if it gets too cold, it's going to engage the HVAC system to heat the building up. So that's in between that zone is typically called the deadband. So normally under a non-reactive system, it does not do anything inside the deadband. It actually waits before it actually hits either the cooling set point or the heating set point before it actually engages the building HVAC system. But as long as it's within that deadband, it's happy. It's almost like driving a car blindfolded if you have the rumble strips. As long as you're driving along and you're not hitting a rumble strip, you're fine. But as soon as you hit one, you'll veer back into the lane. And if you hit the other side, you'll veer back. And that's essentially what an HVAC system does that's reactive. But what you can do now is I don't have to wait for 45 minutes to know that that temperature is going to exceed its set point, its cooling set point. I can actually start making micro adjustments now to try to keep that temperature within the deadband. So now instead of the deadband being an area where you don't make any control, you actually are making controls to try to keep it within there for the maximum amount of time. So it's every 5 minutes, it's looking at the data, it's looking at its projections, and then making a whole new fresh set of control moves. And that's really basically at the heart what an AI system can do. But prediction is actually, a lot easier than the actual control, because once you start making control moves, now you're actually affecting the future. So it does have to take a look at different operating parameters. So imagine not only is it looking at the temperature, but it's also looking at your energy utilization. If you have any peak power rates, so you don't want to exceed that, which could cause your building to pay for higher energy throughout the entire month if you hit a particular peaking rate. And it also doesn't want it to cycle, warm and cold. So it's also looking to balance all those four operating parameters to have the most efficient system as possible. So looking at a case study. So here's a building. It's roughly a 50,000 square foot building. And if you're going to do a before and after with artificial intelligence and without, you want to make sure the outdoor air temperature is as consistent as possible. You don't want one week that's at 70 degrees and another week at 50. So in this particular instance, you'll see this was earlier this year. There was a week where the average was 60.3 and the second week was 60.5. So hard to get much better than that. So even if you look at the load profile from day 1 to day 7, it actually has a similar shape even. So this case study, I think, is very relevant because all the outside conditions are identical. So here, there's a couple pieces of equipment we'll look at. One is the fan power boxes. So if you look at the aggregated fan speed, you'll see that without AI, the average utilization was 62.3%. And when artificial intelligence was enabled, that dropped down to 14.6%. So you had almost a 75%, three-quarter reduction in the utilization of the fan boxes. Next to chillers, you look at was comparable. In fact, the AI was actually a little bit warmer than without the AI. So it was able to make those operating conditions with warmer chiller water, which also provides tremendous energy savings. And if you want to look at across whole different types of equipment, from the aggregated heaters to the fan run times, the compressor run times, you see across the board, there was an efficiency and a savings garnered by each and every one of those. And what that totaled up to from an energy savings is that week without the artificial intelligence, the standard building automation control system utilized over 4,400 kilowatt hours. And when you enabled the artificial intelligence, it dropped down to just over 2,800 kilowatt hours. So that's a 36% reduction in the energy consumption. So not only are you saving money, you're certainly reducing your greenhouse gas emissions. And as I showed before, you're actually making your building more comfortable because now you're not having the wider temperature swings that you had in the past. And since we're in Maine, I thought I'd kind of take some average type buildings, right? So, we have smaller municipalities in a lot of other states. But I'd say a typical municipal building, a library, a town or city hall could be in the 50,000 square foot range. So that, from an energy savings perspective or a financial aspect, you would probably expect to see about a $20,000 reduction in your cost. And that's assuming that you have somewhere in the $80,000 to $100,000 energy cost for that size building. You're also going to reduce your or improve your comfort by 50%. So that means 50% more time you're actually going to be within that dead band. So you're going to be within the cooling and heating set points, as I showed before. And you should expect a 30% reduction in your greenhouse gas emissions. And if you look at a school, which tends to have larger buildings, I think the Maine state average in schools is roughly 180 square foot per child. So if you have maybe a larger Class B or a Class A, a smaller Class A school with 1,000 students, your savings could be upwards to around $80,000 in savings. Also, you get the benefit of the comfort, which, and if you look at that, could have as much benefit, I think, as the energy savings, because we put a lot of effort and time in making sure that our schools are actually the most conducive place for learning. So there's a lot of attention paid to the lighting levels, color temperature of the lighting, but the heating and cooling also has a big impact. Very distracting to be hot or cold inside of a school while teaching. And of course, a lot of schools and a lot of communities have their own greenhouse gas emission targets, and that would allow them to achieve those as well. And I do show one of those is actually a city hall in the city of Auburn. So there's AI is being deployed across the country in different types of industries, but I do want to say and shout out to the city of Auburn because they're actually implementing artificial intelligence in their city hall. So with that, Alicia, I'd like to open up. If there are any questions, I'd be happy to address them now.
Hi, Mark. I'm not seeing any questions, so I should remind everyone that to please put any questions into the Q&A at the should be at the bottom of your Zoom menu, and we will take them as they come. But I'm not seeing any right this moment.
Okay. Well, if any come in now or in the future, you can feel free to. I'm sure if you pass it along to Alicia, she'll pass them on to me, or feel free to email directly as well.
And it looks like we do have one coming in, so let's give it a second, I suppose.
Okay.
Yeah. We do have a few that have popped in. Let's see. All right. Would AI help with a poorly designed system?
Well, AI can only work with what it has, right? So if it's poorly designed, it's not going to be able to overcome any particular mechanical inefficiencies. It does work on top of an existing building automation system. That's probably important to note, is that this is not a building automation system. It actually would sit on top, and there are standard building protocols, typically BACnet or LawnWorks or sometimes Modbus. And so it needs those sorts of protocols to communicate down to the individual pieces of equipment. So yes, it should be able to improve, a poorly designed system. To what extent, it really depends on whether it's, the piping or the heat exchangers aren't necessarily in the right locations or have the right settings. Some of those things it might be hampered, but it still should have the relative improvement. So from whatever it's currently at, you should probably still expect to see a 25% reduction in what your current energy bill is today.
Sorry about that. I was muted. So we do have a few more questions.
Okay.
And there's a couple about cost associated with installation. So one, just, cost of a typical install versus, cost associated with installing a larger, doing a larger project with a central HVAC system. So 50 to 100,000 square feet.
Yeah, no, excellent question. So there's generally no installation cost whatsoever. Really, because I mentioned before, it does essentially utilize the existing building automation system as the communication network to talk to the devices. So these are generally cloud-based systems. And you either need a driver that enables that communication, or sometimes there will be a small box that really is a communication interface from your building automation system to the cloud. So they'll use an APN, a virtual private network that's secured, and but there's no on-site requirements. Typically, your own facilities management team can install the box in an hour or two, and but there's no. And again, you do not actually change any of the programming of your building automation system. So at any time, you could revert back to where it is today. So you're not changing the logic, you're not changing the program, and the algorithms are actually layered on at the cloud level. So there's generally zero installation cost. And what I've seen is generally a kind of a SaaS model, a shared savings model, so that the customers are cash flow positive right from day one.
Great. This next question, you kind of are just answered a bit. So it's more technical. So are there sensors in individual rooms? Where is the brain in the HVAC system? Is it, a computer system? How does that work?
Yeah, so the artificial intelligence and the brain, so to speak, would actually be hosted in a cloud environment and then access the local building controls. But you're not actually adding any sensors. So it's whatever sensors the building currently has. So if you've got, and it'll utilize any existing temperature sensors, all the information coming from whether you have rooftop units, VAV boxes, all those control points and all those sensor points are being aggregated, but you're not adding any additional sensors to the building. So there's no cost or installation effort required there. You're merely utilizing your existing network as it is.
Okay, let's see. So if a town, we've talked about some larger, you mentioned some larger projects. So if a town office is smaller, would the savings to them be about the same percentage?
Yeah, we've seen, everything from, 57-story high-rise buildings in Houston to, 30, 40,000 foot smaller private schools up in Montreal. So we've seen a general reduction in energy of somewhere in that 25% range with all different types of buildings. And that includes hotels, retail, office buildings. It's been fairly consistent. So if you have a smaller building, then you would have a smaller energy annual cost. So your savings would be less, but from a percentage standpoint, they should be the same.
Great. So this next question, I believe you already said that there aren't actual sensors and you're not adding sensors. So it's using whatever system you have. But so this question, this is about, how many people are in certain spaces, and if the system can kind of identify, based on body heat, a difference between a conference room with one person versus a full room of 12 people. Does that have an impact?
So if there are occupancy sensors in the building, it can utilize those. In times when they don't have that or limited, it can use like Google Popular Times, which aggregates occupancy data in common areas, right? So if there are, it won't do it in private areas, but if there are public areas of the building, it can provide that up. And then generally you would also provide it what your occupied schedule is. So if it's a town or city hall and your normal hours are from 8 in the morning to 5 in the afternoon, you can provide that information into the programming logic as well. So it would intuitively know that there's, a higher occupancy rate during those hours. And that's when it would actually make the optimize. So if it knows your people are going to start coming in at 7, it may start base loading at 6:20 or 6:30. So it's going to make that decision based on what's the temperature of the space, what's the weather. So maybe on a January, February, it needs to start earlier to warm that space up to desired levels. But yes, it can make use of occupancy sensors if they're there. But you don't have to add any new sensors to the building.
Great. So do you think that this technology would be useful, or could it be used, in schools, or, would it have an impact on, COVID, with, a lot of schools have been closed because they have old HVAC systems. Would this help to indicate, would it promote, better airflow?
Yes, yeah, and that's a topic near and dear to my heart. So my wife is a teacher here in Maine, and I have 4 children. So it's been a tough 14 months for all of us, and it certainly can help. So some of and there's typically a lot of different algorithms that can be layered on top of a building. One of those is actually a airborne virus mitigation program, AVMP. So what that would do. Now that's going to actually increase your energy consumption, right? So you're going to be bringing in more fresh air, and you're going to be operating the equipment to closer levels that the CDC or hospital guidelines are. So you have much more fresh air exchanges, and that's going to actually increase your energy consumption. But that's not what that algorithm is worried about in regards to that particular one. That's more of a health and safety. So you can actually utilize artificial intelligence to improve the air quality in regards to airborne virus mitigation.
All right, and the last question that we have, unless there are others, if people want to submit them, please do. We still have some time. The last question, maybe we've already sort of addressed, and I'm not 100% clear on its intention, but maybe Mark, you will be able to tell. So the question is, how responsive are systems to requests for changes in the parameters if needed?
I'm sorry, could you repeat that, Alicia?
Sure. How responsive are systems to requests for changes in the parameters if needed?
So if I understand this correctly, right? So generally an AI system will be writing down to the individual building controllers every 5 minutes, right? So it's making that prediction 2 hours out. It's saying, what do I make for a micro adjustment now so I don't exceed either my cooling temperature set point or my heating? So when it sends that control set point down to the actual individual pieces of equipment, the responsiveness of that device or that controller is generally, is how well the facilities team has the PID tuning, right? The proportional integral derivative. And that's how you kind of tune a controller. So that's still needed. This doesn't by any means, remove the need for programming and tuning of the building automation system. But it's certainly going to optimize the control algorithms. And it should actually improve in your long-term maintenance as well, because you're not running your equipment as hard, and you're making smaller changes over time as opposed to larger, more aggressive changes. Once you hit a particular set point.
Okay, let's see. We don't have any more questions. We do have, it looks like a couple of hands are raised. So if you folks have questions, we do ask that you type those into the Q&A. That would be great. Otherwise, it looks like we have no other open questions, Mark. So anything, oh, wait. One more question just popped in. How widespread is the use in Maine at this time?
In Maine, particular, it hasn't been widely adopted, right? So I think the city of Auburn is actually one of the first, but across the country, and actually, I know it's being used in over 16 countries on 5 continents. So every sort of environment you can imagine, from universities in Texas to shopping malls in Australia to Holiday Inns in Canada. So. It has been widely deployed, but to my knowledge, anyways, there aren't terribly many that's currently in the state of Maine.
All right. Well, if there are no other questions, anything you'd like to conclude with, Mark?
No, I just want to thank you and the Maine Municipal Association for this opportunity to talk about artificial intelligence in buildings. So I look forward to hopefully having a booth again this fall.
Great. Yes, we're hoping for that as well.
Great.
All right.